Imagine for a moment that you're holding a glass of water. Try to describe to yourself what you might feel. Can you feel the shape of the glass? Is it smooth or textured? Heavy or light? How cold is it? Do drops of condensation begin falling between your fingers? What about the water inside? Can you sense, by moving the glass, how full it is? Do you feel the light clink of ice against the rim? The sense of touch is a truly remarkable superpower that we use not just every day, but almost every instant of our lives. For every object we pick up, our hands send spectacularly detailed information about its weight, texture, temperature, size, and shape to our brains, along with a constantly updated report of how we're holding it. This information helps us to know how best to interact with our world so we don't burn ourselves on a hot mug of coffee or drop something slippery. Well, in theory. It is estimated that almost 1 in 50 people live with a form of paralysis or injury resulting in the loss of function of one or more limbs. Adding to that nearly 10,000 new amputees every year, over 500,000 people in the UK, and rising, have impaired or absent mobility and sensory function. Help is at hand, however, as a few very smart scientists and their teams of researchers are working to develop more and more sophisticated technologies that could restore movement and even sensation to this group of people. First prosthetics, like a surprising number of things we still use to this day, can be traced back to ancient Egypt, where functionless fibrous limbs were constructed for the use by amputees. Although predominantly cosmetic, there has even been found one case of a functional prosthetic toe on an Egyptian mummy. From there came the pirates' favourite hook hands and peg legs, both rudimentary forms of prosthetic, and then a gradual shift from the 15th century onwards towards more functional and mechanical limbs. The most advanced prosthetics that we see today can use electrical signals from muscle fibres or even directly from the brain to perform more and more complex tasks. We're moving ever closer to creating truly remarkable bionic prosthetics which can closely emulate working limbs, but there remains one big hurdle. Imagine once again that you're holding that glass we talked about at the beginning, but this time you can't feel anything. Not the position of the glass nor the strength of your grip. Unless paying close attention, you could easily crush or drop anything you're holding. And with the increasing complexity of artificial limbs comes increasingly delicate components, so sensing whether that cup of coffee is maybe a little too hot becomes vital for the safety of your new arm. With no sensory feedback, it becomes immensely difficult to know how we are interacting with our environment. But how on earth can we record all that sensory information from a prosthetic and relay it back to our bodies in a way it can understand? We can read information coming from our nervous systems with a reasonable amount of clarity using electrodes or imaging, so how do we reverse that process? There are currently 3 different methods working towards that very goal: connecting the sensors in a prosthetic to the nerve endings at the stump of an amputated limb, rerouting sensory information via intact nerves in another part of the body, or implanting electrodes directly into the brain and stimulating the sensory cortex. We're going to look at the amazing research surrounding each of these and what they could offer us in the future. Meet Professor Horch from Utah. Hello. His team works with amputee patients to create artificial limbs which communicate with the median and ulnar nerves in the stump of the forearm. Using electrodes called cuff electrodes, which wrap around the target nerve so as not to damage it, sensors within the prosthetic can relay information about touch, or tactile sensation, and hand movement and position, proprioception, back to the nerves of the arm. Movement is performed by contracting the muscles in the stump that would have connected to the hand, and information from the hand sensors is then relayed to the cuff electrodes to hitch a ride back up to the brain. 2 subjects were asked to use this prosthetic hand to identify, blindfolded, between 9 objects of varying size and firmness, ranging from a small soft sponge through to a larger piece of wood. One of the subjects was provided with only tactile information, while the other was given both tactile and proprioceptive input from the hand, essentially able to interpret where the hand is and what it's feeling. The second subject was able to successfully discriminate between the size and compliance, a fancy word for squishiness, of the 9 objects. Horch's team showed that even after the loss of a limb, the sensory pathways involved in touch and proprioception are still intact, and, moreover, we can interact with them to produce new sensory stimuli. But as we develop more complex neuroprosthetics that will require regular maintenance, will implanting electrodes into muscle be as viable an option? And will they be able to produce the variety of signals that we'll need for full movement and sensation? What if we could find a way of rerouting sensory information to get the body to do some of that work for us? This is Dr. Kukin. Hello. His team has designed a form of prosthetic control called targeted muscle reinnervation. And what does TMR do? Let's take a patient with a shoulder disarticulation, so an amputation of the shoulder joint, and make them a prosthetic arm. Now, unlike our hand amputee from earlier, we don't just have a few nerves leading to the hand that we can plug into, we've got all of the nerves for the entire arm. So instead of plugging loads and loads of electrodes into each nerve, we can take one of the muscles that would have aided in the shoulder joint and reroute the ends of the nerves into that. When our patient thinks about flexing their phantom arm, the signal will pass through the new muscle and activate it, amplifying the signal. By then connecting our prosthetic up to here, we can piggyback off the naturally, well, sort of, amplified signal to produce a multimodal motor control. There's a bit of an odd side effect to TMR though. The team's first patient, with nerves routed to his chest muscles, was experiencing some odd sensations. When the reinnervated part of his chest was touched, he felt something on his palm. Another area felt like his forearm. The motor control of his phantom arm wasn't the only thing that had been rerouted. His sense of touch had too. This amazing coincidence allowed them to develop a prosthesis that could send sensory signals to a mechanism that then stimulated these newly innervated areas. The only problem of this is that the sensory map doesn't exactly translate as gracefully as we would hope. It's all a bit jumbled. This means it's a pretty big task for every new patient to gradually build a picture of what their rerouted sensory map is like before the prosthetic can work effectively. But wait, however useful, neither of the techniques that we've talked about could work for someone with damage to those vital nerve pathways between their brain and their limbs. For that, we need a way to skip straight past any severed spinal nerves or broken pathways due to neurodegeneration and communicate directly with the sensory cortex of the brain. Our last special guest is Professor Nurmika. Hello. His team works with rhesus monkeys to explore the potential for machine-brain interfacing. Most recently, they've begun to use stimulation of genetically altered cells by light, a method called optogenetics, to activate the sensory cortex of their monkeys. Whilst teaching the monkey to lift their hand from a button when they feel a vibration, the researchers isolated the part of the sensory cortex that was producing the signal that told the monkey, hey, this thing is vibrating. By then genetically altering these cells to activate in the presence of light, an implanted fibre optic could successfully reactivate those cells to make the monkey feel a vibration even when it wasn't there, and thus lift its hand. It'll be a long while yet before we see this kind of light-activated sensory stimulus in humans though, and some of the problems we could face in the future of true sensory prosthetic development seem nearly impossible now. Electrical stimulation almost invariably causes activation of the cells adjacent to the one that you're actually stimulating. And as the demand for more directed sensory input increases, electrical spillage like this could put a cap on the level of sensory precision that we might be able to create. And will we ever be able to emulate the full range of sensory experience that we take for granted every day? This technology is very much still in its infancy, but the possibilities as it becomes more advanced are mind-boggling. We are on the verge of creating the bionics and machine-brain interfaces that only decades ago existed purely in the realms of science fiction. Who knows? Maybe we'll pilot robots with our minds, or create whole replacement, fully functioning bodies for ourselves. But right now, the most exciting thing about neuroprosthetics is their potential to give the gift of touch back to those who have lost it.